As promised, we're going to start talking about the line emission spectra, where we see these discrete spectra that show up. Down here below, the image that I've chosen for us here is actually some spectra of different stars from the night sky. And I think one of the first things we think about of stars in the night sky is they're kind of little white dots. But if we actually look at their visible spectra, we'll see that that's not always the case. So sometimes you see that there are missing segments that are in these stars, these dark lines where light is not coming through. This is actually a really important idea and development so that we can actually measure things and understand their molecular structure. So if you ever wanted to know, for example, what is on the inside of a star, spectroscopy is our major tool. And understanding line emission spectra is kind of the key to understanding that. So just as a reminder, we talked about the differences between, say, a continuous spectrum, and down here we have a discrete spectrum. The continuous, there's no gaps. There's a photon at every point across this plot. There are no gaps. But we saw that there are some spectra where we do get these different types of looks, where here we have just a red line, a blue line, the indigo line, and the violet line here. This is specifically for the case of hydrogen. So if we take atomic hydrogen and we add energy to that hydrogen, we'll see that what we end up getting is light that gets emitted from our hydrogen. That's kind of cool. But it's very specific in what types of light gets emitted. It's these 4 different lines. Okay, truth in advertising, there's more than just 4 lines. But what I'm just showing here is the 4 visible lines that we see from hydrogen. So why is this a thing? What does it mean? How do we interpret this? Why is this useful to us? That's what we're getting into today. So hydrogen was really the first line spectra that we really understood well, and this goes back to the late 1800s with Balmer. Balmer was a scientist that was interested in light, specifically only looking at the visible emissions from hydrogen. And he was wanting to know, is there some sort of pattern that predicts these colors that come off of hydrogen? And through some really good work, he was able to say, hey, the frequency of our light here, which is just 1 over the wavelength, could easily be represented by a constant R multiplied by this interesting unit here where we've got 1 over 2 squared minus 1 over n squared, where n is just an integer greater than 2. So it could be 3, 4, 5, so on and so forth. So that is the first kind of indication that something weird is going on here. We're so used to thinking about light as a continuous beast, but all of a sudden we're saying, hey, it can be explained if we use only integer values. That's a strange thing. It's not continuous. It's discrete, as we would say. So that was a really important finding here. And again, it just needed one constant, and right now it seems completely random, this weird number here, but we'll talk about that here in just a minute. But this was a first indication that there's some really important science here, this weird discrete value system that's showing up to explain the visible lines of hydrogen. Couple years later, second scientist Rydberg comes along and is now looking at all of the emission lines. So this includes the infrared and lower energy photons primarily. Finds the same type of relationship and says, hey, wait a minute, it's not just for the visible, it works for all of our emissions. The only substitution we have to make is now, instead of 2 squared, I have n1 squared, where n1 is just, again, an integer. It can be 1, it can be 2, and so on and so forth. Now, n2 is also an integer, but it's slightly different. It has to be greater than whatever number that you have here. So if you start with n1 as 1, the lowest n2 would be 2. If you started, for example, with n1 equals 2, then it could be 3 or higher. But again, we see that it continues on in this discrete pattern. So two different scientists working relatively independently come up with the same cool relationship using the same constant, and it describes everything about hydrogen. Again, that's a clear indication that something interesting and useful is going on here. That funky constant here, this Rydberg constant as we'll now call it, is actually found to be just a collection of constants. 2 pi times the reduced mass, don't necessarily worry about what that means, times the charge of the nucleus, times the charge of the electron to the fourth, and then you've got some more things down here. This 4 pi E0 is just the permittivity of a vacuum. And then again, H, Planck's constant, showing back up again. These are all the things we have to deal with here. So R's not random. It's actually related to fundamental physical quantities. Okay, now obviously something is really useful here. So this was the first key. So even in the late part of the 19th century, we're seeing that the world is more complicated. We used to think in this period that everything was continuous, but we're seeing that is not the case. When we look at things like emission from elements, they are this weird, discrete type of system, which we now start to say that it's a quantized system. We'll talk about quantization at another point. If we want to put this all into a plot, what we can actually see is that hydrogen is easily explained in a simple plot, if you will. So if I look here, we have a series of lines here in green, which are referred to as the Balmer series. And what we're showing here is that the physical process going on is that the hydrogen starts with some high energy and then drops down to this lower energy state. And as that happens, we emit photons. And that's what's always occurring in these. So all of these lines that were seen by Balmer and fit to that equation, this is what's actually happening. They're all coming down to what we would say is the n equal 2 state. So it's the second lowest energy state. So second lowest energy state. Over here to the left, we have the Lyman series. The reason that this one wasn't really seen by Balmer is that it's actually in the ultraviolet, so it's a much harder measurement to make back in the 1880s. But it follows the same pattern. We start from some high energy level, and we all drop down to the same level down here, down to n equals 1. There's a whole other series that you can look at. You got the PChem, you got the bracket series. These are both in the infrared. And that goes on and on. You can find more of these, but it all follows that same pattern. And then we can just use our basic equations to relate the arrow length, how much energy is there, to what the wavelength of the photon actually is. So super important, critical dissemination of what hydrogen's actually doing in its electronic structure. And this understanding that was the foundation was laid back in the 1880s was really picked up by the Bohr model, which we've already discussed. And I will go ahead and tell you, it's ultimately wrong, meaning this is not the true physical nature of the hydrogen atom, but still useful to how we think about it. So the way to think about it, as Bohr said, is these energy levels have specific orbits around our hydrogen nucleus. And when we are having energy going in or coming out of the hydrogen, it's because we are jumping back and forth between these levels. Energy has to go in, it has to be absorbed to go to a higher energy level. It has to be released to come down energy. Remember, energy is always constant. We can't get rid of it, we can't destroy it. It has to go somewhere. Where does it go? It goes around as photons here. And these all connect back to those photons that we're seeing coming out here. So this was where Bohr's planetary orbit model really came from, is the recognition that, hey, we had these observations by Balmer, by Lyman, on saying, hey, these are all valued, but it also does connect to the geometry of the system. We're seeing now that the electron can be in different places, and those have different energy levels for us. So that's the importance of line emission and what it's telling us about atomic structure. It basically gave Bohr what he needed to come up with that planetary model that we use so frequently to understand atomic structure. Again, we're going to see that since Bohr, things have changed. We've gotten more data. We know more. So we'll talk more about the current models in another video, but that's what we need to know for now. All right, so I think that'll do it for this one. As always, if you've got questions or concerns, let me know. Let's talk about it. Let's make sure you understand how line emission spectrum are useful and what they mean. But until I see you next, be excellent to each other.